Okay, so let's get started. What do all of these swimming pools have in common? Well, they're very energy intensive. There are different reasons for this. Partly we're dealing with very high temperatures around 30 degrees or even warmer, which means a swimming pool hall, you have to heat them all year round. In addition to that, we have quite a lot of heating demand for water, whether it's the actual pool water itself at 28 or 30 degrees, but also the showers, people showering before and after they go for a swim. In addition to that, we have to deal with the humidity loads from the evaporation from the pool, which has energy implications. We have the technology to keep the water clean and safe for swimming, which also requires energy demand. And then often in leisure centers, we have additional activities, whether it's a sauna or a gym or so on and so forth. Quite often in leisure centers, we have more of those facilities. All of this adds up, and we have buildings that are very energy intensive and very costly to operate. That also means we have a lot of potential here to improve things and actually achieve significant amounts of energy savings. So we did take a deep dive and see how can we actually go about this. It's very clear from the outset that the standard passive house criteria, so the 15 kilowatt hours per square meter and year that we're familiar with for passive house heating threshold, physically is just not possible for a swimming pool. It doesn't work. So how do we go about it? We say, well, passive house is a holistic approach. We say, okay, we have a certain service that we want to deliver as part of this building. How do we optimize the building as a whole? Looking at the envelope, looking also at the technical systems, looking at the controls. How do we optimize it as an all, as a total system to be able to provide that service with minimum energy input? That's the general approach. And we were very fortunate that in 2009, when this whole journey started about passive house for swimming pools, we were approached by a municipality in Germany, and they said, we want to explore this. We want to see what the energy savings are. We got funding for a research project based on an example of a real-life project. That was the first pilot project built in Germany as a swimming pool to the passive house standard. A second one quickly came on board, and these first two pilot projects, the Lippebad and Bambados, they both opened their doors in 2011, implementing these energy-saving strategies that we'd researched and developed together with the teams. As proof of concept, which is super important in order to move things forward, we had 2 years where we were able to monitor both of these projects in quite a lot of detail to check what the actual energy consumption is and whether the research that we'd done in advance was turning out in practice. So that's kind of the step that we took starting 2009. A quick overview of the story of success for both of these projects. This is the Lippebad, which is a fairly straightforward project. It has 5 pools, but no kind of additional leisure facilities. And this is the Bambados project, which is larger. It has 7 pools overall, and it has also a sauna and a spa facility included. So those are both two projects, and both of them are very successful in terms of the energy savings. It's extremely difficult in this kind of typology to make any comparisons for energy savings, but if you compare the projects to similar typologies, so to buildings with similar sizes of pools, then in both of them we achieved savings for the heating demand at around 60 to 65%, which is the red, and for electricity between 20 and 46%. So really substantial savings, reduction of energy consumption that we achieved with these 2 pilot projects. So those were very successful, very, very popular. Which meant we were able to continue our research, build on what we'd done, see what additional energy savings we had, and we had additional municipalities coming up to saying, this is really interesting, how can we implement this? The third project that's come online is the Exeter City Council project, which actually opened its door last year in 2022, and is the third passive house project which is now in operation in the UK. What's come out of all our research work? So while we were consulting on the project in England, while we were doing additional research work, we consolidated all of that into a guideline booklet because we wanted to make sure that all of this information is published in a way that future projects can take this on board and implement those energy saving strategies in their project. And it's this guideline really that I'm going to present to you in a very, very condensed form today to give you an outline of what the energy saving strategies are. We now have quite a lot of interest, especially in the UK, because that Exeter project has raised a lot of interest. So we're working on a number of projects in the UK now implementing these same energy saving strategies. So this is the guideline. It's published in both German and in English. It's available for free for download on Passipedia online. And it covers different aspects of energy saving, starting with the thermal envelope and thermal zoning within these buildings, but also looking at aspects such as the water treatment, such as the ventilation strategies, just generally energy efficiency strategies, and also aspects of controls and operation to ensure long-term energy savings. And as I said, I'm going to give you a very quick, condensed version of those main topics, but I do encourage you to go ahead if you're interested in the topic and have a look at those guidelines. So starting out with the thermal zones, this is really the starting point. When you design a building, a leisure center or a swimming pool, think about the different temperature zones that you have the building and think about the layout that you're going to have. If you want to build an energy efficient solution, that's your starting point to make it cost effective and also functional. So this example from the swimming pool in Lünen, we've got the warmer temperatures, 30, 34 for the pools. Down here, facing towards the south, then this is the buffer zone, that's the changing room around 28 degrees, and then your 20-degree entrance area there. It's a fairly simple layout in this case, but that makes everything else a lot easier and a lot cheaper also to build along the way. Something to keep in mind is you might also need thermal separation within the building itself, which you don't often have in a passive house, but you do in this case, in order to separate out these different zones. And also something important to keep in mind is to try to align your ventilation strategy with these different zones. So maybe you have a different ventilation unit for each of these usage zones. In terms of the thermal envelope, I won't dive into too much detail because it's the same principles as we are familiar with the passive house. It is slightly more strict. So for a pool hall, we're looking at U values of around 0.1 watt per square meter in Kelvin. What's really important here is that we need to avoid damage to the construction. So we have slightly stricter requirements for the thermal bridges, which is here outlined in the FRSI factor. In terms of air tightness, again, we're a bit more stricter, which is mainly because we're dealing with warm and humid air and we want to protect the fabric. So for air tightness, we have a slightly stricter requirement than in a conventional passive house building. And the development in UK, for example, they were very scared when we issued or when we said this is our target that you have to hit for the passive house certification. But all three projects managed to hit this without problem. This is the example from the Bambados, which had an N50 of 0.07 air changes, which is an incredible result. So it's doable if you know from the outset that that's what you're aiming for and you have good quality control on site. So starting kind of overall, passive house envelope is our kind of entry door to energy savings. If we implement those 5 pillars of passive house that we're familiar with, we already achieve quite a lot of energy savings by that because we've reduced our transmission losses. The really nice thing here is with the energy efficiency concept for pools is that the envelope is kind of the starting point and enables you to dig deeper and really achieve more energy savings by changing your mechanical systems on your controls as well. Part of that is we now have a much improved thermal envelope, which means there's much reduced risk of kind of any condensation or mold on the facade, which means we can change the concept of ventilation in these pool halls. Conventionally, pool halls are run with very high rates of ventilation throughout the year, as we can see in this graph here. The blue, what you see, this is actually measured from one of the projects. The blue here is what we need for dehumidification. So that physically is what we need over the course of the year. In winter, it's quite low. In summer, it's high because we have higher dehumidification demand. In green here in the background is what in a conventional pool you run throughout the year just as additional recirculation, because in a conventional project you need that air movement. We don't need that anymore in a passive house pool because our envelope is so good. So we can cut out all of this green part, which if you translate that into electricity consumption is quite significant. So there's an additional amount of energy saving there just by cutting out the recirculation air. In addition, because we have a really good thermal envelope, it means that we can raise our humidity level at which we operate the pool. Raising the humidity level has different advantages. One significant one is that we have less evaporation. Less evaporation means less heat losses from the water. It also means less dehumidification demand, which means less ventilation, so on and so forth and so forth. As I said, it gets quite technical, but the quintessence here is that because of that better thermal envelope, because of the higher humidity again, we tap into more energy savings for our heating and electricity. Okay? So that was a quick run through in terms of the main starting point for the pool hall. Obviously, there are many other energy consumers in these types of buildings. It's not only about the swimming pool hall. There are other energy consumers as well. So what you see here in this graph is the energy balance of the Barbados project, showing the different parts. Here on the right-hand side, this is electricity. On the left-hand side, it's the heating demand. This is mainly the pool hall heating. Obviously, some of the areas also need heating, but dominated by the pool hall heating. The other big part that you can see here is the heating demand for the pool water, which is kept at high temperatures for swimming throughout the year. In the Lipperbad, that made 40% of the overall energy consumption. In the Barbados, 43%. So again, it's something where it's worth really diving into details and seeing how can we bring that energy consumption down. So what we did is we set up an additional tool that lets you calculate the energy balance of such a pool to look at kind of what are the heat gains, what are the heat losses, how can we optimize this and try to bring the energy demand as low as possible. And again, there's a lot of detail that goes into this. Summarizing right now, just the main points of action that you can keep in mind. First of all, obviously, the temperature of the water. The lower the temperature of your water, the lower the heating demand. And this is quite significant in this case. So consider as an operator lowering the temperature. Obviously, that's a matter of the use of the building and also of the comfort. So you might not have too much leeway there, but it's something to keep in mind. The other aspect of the rate of evaporation, as I mentioned earlier. So evaporation consumes quite a lot of energy for the conversion from water to gas. So we try to reduce the evaporation as much as possible. One measure for that, as I said earlier, is to increase the humidity level of the pool hall. There are other measures that you can take, for example, looking at kind of the overflow mechanisms of the wall of the water at the edge of the pool. So that's something to look out for. Then last, but certainly not least, one of the main important most important aspects that decide your energy demand for the pool water is how much fresh water you have to bring into the pool in order to maintain its quality. And this, quite interesting, is often not driven by the amount of people that you have in the pool. It's actually driven by the choice of your filtration technology. So depending on what filtration technology you use, you have to keep those filters clean. You have to backwash them on a regular basis. And the choice of that filtration system often drives how much fresh water you're constantly bringing into the system. So it's worthwhile when you choose your filtration system to be aware of what kind of water demand that means. Now, the Passive House standard, the way we approach it, we don't prescribe a specific filtration system because there are different reasons for using different filtration systems. We do look at what the implications are in terms of energy needs. And if a filtration system of choice needs a lot of water, which means higher energy demand, then you have to compensate that by other means, for example, by using heat recovery on your wastewater for the pool system. Okay? So that's a quick run through on the actual water heating. The other aspect for the water is the electricity demand that you have for the constant water treatment and water circulation. So in order to keep the water at a high quality, we have to circulate it basically 24/7, keep it in movement. You have to filter the water, you have to disinfect it. Again, there are different technologies to do this. We don't prescribe a specific one. What we do look at is what is the electricity, what is the actual energy demand to be able to run that system. Again, lots of details that you can dive into, and as part of the design, it's important to understand your system and the energy implications. One really, really important part here is the pumps for circulation. So all of our kind of energy analysis and research showed that looking at those pumps for circulation is absolutely crucial in order to bring your energy demand down. They run 24/7. You have to run it at a specific rate in order to maintain water quality. What's really, really important here, it's a design aspect. So this is not something you can change later on, but the layout from the very outset of the project, keeping that pipework short, reducing your pressure head, selecting appropriate pumps, is a design issue at the very, very beginning. What we've done as part of our pool guide is to give an energy target here and say, okay, our goal is maximum 24 to 40 watts per cubic meter an hour that you're circulating with that water. And on every single project we've consulted so far, the pool technicians have come back to us and said, impossible. But then when you work through it and you really look at it from the outset, from the design, you reduce those distances. It is possible, but you do have to work hard to do it. But it's super valuable because it's something that doesn't come at additional cost. It's really mainly a design issue at the beginning of a project to get there, and it has long-lasting energy-saving effects. Right. Next topic that we're touching on is our hot water demand. So this is for the showers mainly. There's nothing too spectacular here. This is all technology that we are familiar with from the Passive House scene. There are, again, design aspects that we can keep in mind that don't mean additional costs necessarily, but are just logical in order to reduce energy waste. For example, keeping your pipework short, trying to lower the temperatures of your distribution, working with low flow water heads, those kind of design aspects. Something that we're pushing for more and more, which hasn't been implemented in the pilot project so far, but we are pushing for in the future project or the ongoing projects, is to consider wastewater heat recovery from the shower water. There are more and more systems available. I think there's even some exhibitors here at the conference. I think it's more popular in France than it is in Germany at the moment. But there's a lot of saving potentials here to have wastewater heat recovery from the shower water, just because there's constant shower use in these kind of projects. So it just makes a lot of sense. Right, and then last but certainly not least, we have all this extra electricity demand in this energy balance here, which covers ventilation, it covers lighting, and it covers all sorts of additional equipment. The additional depends very much on your type of project, so what other facilities you include, so I won't dive into details. I do want to touch a little bit on ventilation. Again, the strategy here is the same as what we're familiar with from the general Passive House approach. We have our limit for our electrical efficiency, and we have our limit for our heat recovery efficiency. For the heat recovery efficiency, we do have higher requirements for the pool hall because we have higher temperatures and humidities to deal with. So again, Passive House approach, but a little bit stricter. What's really, really important in these projects, that yes, you might have to dimension the ventilation units to be able to deal with high humidity loads in summer and high occupancy rates, but there's a lot of saving potential here with demand control. So being able to ramp down the systems in winter when it's drier or when you have less occupancy, so that you don't overventilate and you don't have too much electricity consumption for the fans. A big takeaway for me from the projects we've implemented so far, a big learning here, is to try to keep it as simple as possible. There's kind of a trend to try to get everything as detailed as possible, control on CO2 and humidity and all sorts of sensors at the same time. My experience is that that's very difficult to commission and then also to make sure that it's operating the way that you want. So it's better to try to keep it simple, maybe set kind of a low-level ventilation rate that's suitable for low occupancy, and then have it ramp up only when you need it, for example, based on humidity. But try to keep the systems simple as possible. Well, and all the other equipment, obviously looking out for lighting. We have some efficiency guidance for lighting in the tool guide. Then it's things like the saunas, like the lifts, it's all the other equipment. And again, holistic approach of Passive House, important to be aware of that equipment, to model them at the outset, understand the energy demand, and see where the energy saving potential is. Yeah, so it's all about the holistic approach. So what we also have in some of these projects is part of the building might need active cooling, the gym, for example, whereas other parts of the building need heating all year round, whether it's the pool water or the pool hall. So heat pumps technology nowadays can do simultaneous heating and cooling. So you take the heat from one part of the building to heat other parts of the building. So make sure to look at the building as a whole. And as I said, don't overcomplicate. Try to keep the system simple and robust. Now last, one of my last slides is to emphasize also that it's not only about the design, it's not only about the choices of your components, it's also a lot about your controls, it's also about commissioning the systems in the way that you intend them to be. So what you see here on the right-hand side is from our monitoring report from the Barbados project, the electricity consumption for the ventilation units. So when we first started out, they were running quite high. So it took us almost 2 years to work with the operators, to work with the manufacturers of the air handling units to get them operating to the way that they were originally intended, and we were able to bring down the electricity consumption by 60%, which is substantial. So it's really important that before you actually open up the project, you're very aware of what your controls need to be, and you have a good commissioning process, and ideally kind of a soft landing, so you have a period of time where you're also on board and checking whether everything's working the way it's supposed to. And as part of our guidelines, we've also issued some checklists, which you see down here, which help you, A, with the commissioning, but also as support to be able to give to the operators so that they can track their energy consumption over a longer period of time once the project is in use. So, what does that now actually mean? If you're interested in applying these concepts to your project and attaining Passive House certification, Passive House accreditation for your pool project, we don't have a standardized process for this yet. As I said, there's kind of 3 projects that are certified or under certification now. There's a few more in the pipeline. The process at the moment is that we issue qualitative requirements, so that's for your U values, it's for the pump efficiency, so on, so the main things that I outlined in this report. And then in addition to that, we issue, based on a multi-zone PHPP, bespoke energy targets for the pool, right, for the specific building. Because every building is different, we can't have the same energy target for every project. We issue bespoke energy targets for every project. So that's basically the process for Passive House certification at the moment. We have good experiences with this multi-zone PHPP. Basically, you set up a different PHPP model, different energy balance for each usage zone within the building. So one for the pool hall, one for the changing room, one for the gym, for example. And they get combined or coupled to also take into account the heat transfer between the different zones. We have very good experiences with that, and that's what we're developing further. At the moment, that's only within PHI, so Passive House Institute has to do that multi-zone modeling. We are working on templates to be able to hand out to designers, hopefully by next year. Now, obviously, in a pool, there's additional aspects that are not covered by the normal PHPP, so we've developed a pool tool, which covers aspects such as the energy balance for the pool water and the aspects of evaporation and so on and so forth. So that's a supplementary tool that you have to fill in and work with to give you the complete picture of the project. And that already brings me to the end. It's kind of leaving you just with a quick outlook in terms of if you're interested in learning more about this topic or applying it to your project itself. Starting point definitely is to read and inform yourself on the information that's available. The guideline is quite comprehensive. Go ahead. It gives you a good overview. As I said, that's available in German and English. If you do speak German and you want to dive into a bit more detail, then we have published extensive reports on both of those 2 pilot projects with detailed monitoring data and so on. Second step is to actually, if you can, go and visit some of these projects. This project in England only happened because the designers and the municipality went and visited those 2 projects in Germany and was convinced by it that it really worked. And they really learned a lot also from those original design teams. So you learn a lot by speaking to the people who implemented this beforehand. And then last, well, not least, the third point is if you are interested in applying to this project, then get in touch with Passive House Institute or with an accredited certifier in your region, and we work together to consult and help kind of identify what the energy saving measures are and what needs to be done to achieve the Passive House standard. That brings me to an end. Thank you.